Let's add a few more tidbits to the paleoclimate observation. So this is a very long time scale observation of from various evidences mixed together. And this is going back to the time of the dinosaurs, 65 million years ago or so, and showing temperature, polar ocean temperature equivalent change here compared to modern times again, and the proxy from what is called delta O18. Okay, essentially evidences of past temperature change are not direct measurements of temperature itself. They are called paleoproxies because there are isotopes. For example, oxygen has 16 but also 17 and 18, and when evaporation happens, very quickly I'll explain what it is, H2O16 and H2O18 exist because H2O18 is heavier. When evaporation happens, more of the H2O16 gets picked up, let's say, from the ocean. So the clouds will be then enriched in O16 because more of the O16 has been picked up during evaporation. As it moves towards the poles in these cells that we talked about, more of the O18 falls because it's heavier. So whatever reaches high latitudes and falls as snow has lost most of the O18 that was picked up already from the ocean. So the glaciers then begin to get enriched in O16 because O18 is preferentially lost as rain during its travel. Okay, that means when glaciers build, ocean is enriched with O18 because more of the O16 is locked up in glaciers. So these differences can be seen to interpret when it was colder and glaciated and when it was less glaciated and warmer. But you can also see that these wiggles here are much smoother than here. So as you go in the past, the time resolution, the periods you can see in the data becomes less and less. So here you will capture 1,000-year time scale. So the scale here is non-linear. You can see that we go from 0 to 10 million, and then well, this is almost linear, but nonetheless, as we get close to the modern times, we will see that we will use a different time scale. Okay, so we are adding the Vostok ice core data here that we just saw. So you can see that there are many more time resolutions captured here, but also there is a change in time scale happening over this time. So these kind of observations exist. They have to be interpreted carefully. Often models are used to reconstruct past climates. In fact, that's a good test for models to see if they can reproduce past climates so that we can trust them for future projections. Okay, so you can see that it was much warmer in the past during the time of the dinosaurs, when there was no glaciers on Greenland or Antarctica. Arctic was ice-free. Dinosaurs were roaming around in Siberia in the Arctic Circle and so on. So why do we worry about the global warming of 1 degree centigrade if it was so much warmer? Obviously because we were not around at the time. We have only become dominant in the last 10,000 years, where we will see that the temperature has changed basically about only 1 degree centigrade. So are we able to survive such warming? That's the key question. The planet will not go anywhere. Life will survive, but it's a question of whether we will survive. Okay, this same thing now, the same plot here has been concatenated with the modern time. So here we are in the 20th century into the 21st century, and combined with the projections we will look at from the IPCC models that we talked about. So it gives you a sense of where we are headed if we don't do something about reducing our emissions or taking our emissions out of the air. Okay, so this gives you a sense of the various time scales that are there in the system. So we'll talk about the concept called climate sensitivity. If we want to do these projections based on models, we need to understand how sensitive our model is to changes in carbon dioxide especially. So there is a specific definition for climate sensitivity that we will talk about, but past climate data gives us a sense of the intrinsic timescales and tipping points and thresholds that are in the system. Okay, this is zooming in closer, looking at the end of the last ice age. So the last glacial maximum happened around 21,000 years ago, started 130,000 years ago during the Eemian, kept building glacier in that slow cooling phase. Then you can see there was an abrupt melt with a little glitch here called the Younger Dryas, which I'll come back to. But this gives you a sense of how rapid abrupt climate changes can happen in the warming phase. Okay, we will visit to that, but you can get a sense here that little temperature changes around this baseline, the modern baseline, have had serious impacts, like Vikings colonizing Greenland and disappearing, many civilizations here, greening of Africa, and civilizations expanding from the Nile over onto the western Africa and then shrinking back. And on shorter time scales in the last couple of millennia, we have had Mayas, Incas, and so on. So society's ability to deal with these climate shocks has to be understood as well. And here again are the projections we are hoping for, like less than 1.5 degree, trying to avoid extremes like 4.5 degree and so on. So this is the context that we have become agricultural societies and then industrial revolution and so on, over a fairly stable climate over the last 10,000 years. So it matters where we are headed in terms of what our tolerance limits are. So it's not really about saving the planet, it's really about saving ourselves. So knowing the observations, knowing what information can be derived from the observations, and what observations we need to keep improving our projections becomes very critical. This is why we are getting a sense of what observations are available from the past. And we also talked about reanalysis, where models and data are combined to produce a more uniform distribution of essential climate variables, which help us understand the processes, for example, of where the anthropogenic carbon dioxide is going, where the heat is going, how long it may stay there, whether ocean is becoming less of a sink of carbon dioxide, whether its ability to take up carbon dioxide is decreasing with increasing carbon dioxide, where acidification is happening, and so on. All these things can be understood only if we know the sensitivity of the system and the processes that determine those sensitivities. So observations obviously are very, very, very critical.